All right, good afternoon, everyone. Hopefully everyone can hear me. Okay, do we have class on Thursday? No. So today's pretty much the last day for you guys for this week, since Thursday is officially Thanksgiving Day. So no class will be had on Thursday. Yes, but don't forget that you do have an exam coming up. Well, actually, no, it's not coming up. It should be, you do have an exam. Um, this this week, which is the third exam. It should already be posted. Oh, so many things. There you go. It should already be posted, your exam, on Canvas. So if you have any issues accessing it, let me know, but you shouldn't. And that's pretty much it. Any other questions? Okay, now we're gonna start what we're gonna continue section, not section 9 chapter 9. We're gonna continue chapter 9. And then we're not gonna finish chapter 9 today. I was hoping we could, but I don't think we're going to. Having some technical issues with this thing right now. I don't know why. Okay, there it is. So we're gonna do section 9.5. We're gonna finish up on 9.5, I should say. And then start 9.6. And then we're gonna jump to chapter 12 after this. And chapter 12 is the last chapter we're gonna do for this course. Wait, you guys aren't on here yet. I got the wrong notes for you guys. You guys were here. Yeah, digraphs. Okay. But any questions so far? No? Okay. Keep in mind that once we come back to Thanksgiving, once everyone comes back, I should say, hopefully you guys come back. Next week is the last week prior to the final. And the only chapter left for the is chapter 12. And we're gonna do chapter 12. That's it. And most likely, yes, we're finishing chapter 9, most likely on Tuesday, and starting chapter 12 on Tuesday as well. And we'll probably finish chapter 12, to be truth be told, we probably won't finish chapter 12 till Tuesday in 2 weeks. Which means on finals week, you only have one class. We will most likely only have one class session. But I'm also planning on the last week, leaving it all up to just the final. Meaning we may not even, the final will replace the lowest exam, assuming you pass the final, because if you don't, it's not going to help you at all. And assuming it's not due to cheating. None of your lower scores is due to cheating. Because obviously, if you cheated on an exam, you have a 0, and that's the lowest score. So even if you have 2 zeros, none of them are getting replaced. If one of them is due to cheating. Okay, Any other questions on what I just said? No? Okay, I'm just trying to make sure. Now, let's go with section 9.5. Okay. Now we understand what a relation is. A binary relation. So we know what a relation looks like, okay? We've seen this before. A relation is a subset of the Cartesian product of A cross B of two sets. We know that. Now, what makes it, we know what are required for relations to be reflexive, what it means to be symmetric, and what it means to be anti-symmetric and transitive. So we know what a relation needs to look like in order to have one of these properties, right? That's what pretty much we focused on last time. So we know what that is. Okay. This section, we're going to be talking about equivalence relations. Now we're going to start talking about equivalence relations. Okay. Now, what is an equivalence relation? Well, pretty much an equivalence relation is a relation that has a property that's transitive, symmetric, and reflexive. That's what an equivalence relation is. And I'll write that down. A relation on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. So that's what an equivalence relation is. A relation on a set A is called an equivalence relation if it's reflexive, symmetric, and transitive. Okay. Now, so for example, let's say we have the relation under the set. Let's say we have the sets A, E, I, O, U. Oh man, that's a lot of letters. That's fine. Let's say we have the set. Now, this is obviously the set of vowels within the American alphabet. Because there might be other vowels in other different languages. So let's say, or there might not be any vowels. But A, E, O, U are the set of vowels within the American alphabet. Now, if I do a relation of that set, let's say A, comma A, E, comma E, I, comma I, O, comma O, and that's pretty much it. Is this an equivalence relation? Is this an equivalence relation? That's how high up it goes. So would this satisfy the definition of an equivalence relation? If not, why not? If so, then why? But if not, why not? Why is this or is not an equivalence relation? Just by looking at this definition right now. Why is it not an equivalence relation? You're right, it's not an equivalence relation. Why not? It's transitive actually. A goes to A, so then we're looking for anything else that starts with an A and D in this. And if you want to say the x coordinate of the order pair, there's none other than this. So A goes to A, E goes to E. We're looking for another E. No. So E goes to E. So yes, this is transitive. It is transitive. It is not symmetric. It is symmetric though. A goes to A, and then we need something that starts with A and it goes to A. Yes. E goes to E. We need something else that starts with E here and goes to E. Yes. So it's symmetric. All of these are symmetric. It doesn't have a U. What do you mean by U? Be a little bit more specific. UU. In other words, yes, it doesn't have the order pair UU, but why is UU important? So which one of these properties is it missing? Because we already took care of transitive, it is. We already took care of symmetry, it is. Right, it is not reflexive. So this is not reflexive. Since U and U is not in the relation. Exactly. It is not reflexive at all. Okay. But if we had something like this, let's say a different set. Well, no, I can still do, let's say R sub 1. So I'll call this R sub 1. Let's say we have R sub 2, which is a set A, comma A, E, comma E, I, comma I, O, comma O, U, comma U, and let's say A, comma E, and E, comma A. Let's say A, comma I. Actually, no, not A. Yeah, then we have E, comma I, and then we have I, comma A, and I, comma A. No, E. Okay. Well, for sure it's reflexive now because of all of these. Is it symmetrical? AE, EA, yes. If AI, I should find IA in there, yes. EI, I should find IE in there, yes. So symmetrical, yep. Is it transitive? Well, let's find out. AE, EA, which means I have to go from A to A now, yes. AE and EI, which means I have to go from A to I now, which I do. EA, okay, here's an A, so A to A, so I need to go from E to A, which I do, or EA, which means AI, so I need to go EI, which I do not have here. Oh, no, I do. It's right here. Literally right there looking at my face. So far, so good. Anything else? No. AI, so I'm looking for I, so AI, it's right there. AI, IA, so I need to go from A to A. I do. AI, IE, so I need to go from A to E. Do I have that? Yes, I do. So far it's working out. EI, so I need to go, here's an I, so IA, so I gotta go from E to A, which I have. I have I here as well, so EI and IE, so that means I gotta go from E to E, which I do have. So far, so good. Am I missing any other ones? EI, I has to go to I, so E has to go to I, which I do have. IA, AA, so I has to go to A, which I have here. I have IA, A has to go to E, so I has to go to E, which I do have here. And I think I and AI, so I has to go to I, which I have. Awesome. IE, E goes to E, so I has to go to E, which I have here. IE, and then I have EA, so I has to go to A. So I'm looking for IA, which I do have. IE, EI. So I has to go to I, which I do have. So yes, it's transitive. So R2 is an equivalence relation. Because it follows the properties that it is transitive, symmetrical, and reflexive. That's what an equivalence relation is. Let me give you another example. Let R be the relation on the set of ordered pairs of positive integers such that the ordered pairs of A, comma B, comma C, comma D are in R if and only if AD is equal to BC. Show that R is an equivalence relation. Oops. Now let you copy that down. Assuming you haven't copied it yet. Okay. Now, I want to let R be a relation on a set of ordered pairs of positive integers such that the order pair A, comma B, comma the order pair C, comma D is in a relation. Now, what does this mean? What does this mean? Well, think of it like this. For example, for this scenario here, for R sub 2, A, comma I is in a relation. To avoid any confusion, I'll use two different letters. A comma I is in the relation, which that looks like a T. There it is. A comma I is in a relation, right? So remember that what's in the relation is an ordered pair. So this is A, and this is your, you know what, instead of I, let's use E. So you don't get confused either. So this is your A, and this is your B. That's the relation. So in other words, this is coming from set A, and this is coming from set B. And our scenario, in this scenario, though, our set B is the same thing as saying set A. But pretty much these elements are coming from set A, and these elements are coming from set B, from the other set. Good? Does everyone agree with that? We've been doing relations since last time. Yes? No? Okay, because I'm trying to make sure you understand this next part. So if you have this thing here, another way to look at it is this is coming from set A and this is coming from set B. So this is the ordered pair A comma B. So it's like saying this is your E and this is your I. The only difference is that each one of these is an ordered pair as well, but it's the same thing. So if I want to show that this is an equivalence relation, I have to show three things. One, I have to show it is reflexive. Reflexive means A R A. So I want to show that this is reflexive. Okay. Well, So I'm going to choose an element, A comma B. So suppose if the order pair A comma B, comma A comma B is an R, then by the definition of the relation, we have A times B is equal to B times A. But A times B times A, but A times B or AB is equal to B times A, or BA is the same thing as saying AB. Let me rewrite that. So, but B times A is also the same thing as saying A times B by commutative property. So A times B is equal to A times B. Hence, R is reflexive. So we have A comma B, the order pair, and the order pair A comma B and R. Then by this relation, AD is equal to BC. So I'm doing the same thing, AB times ABA. But BA is the same thing as saying AB. So A times B is the same thing as saying A times B. These are equal. So this is reflexive. Does anyone agree with this? Okay. 2, is it symmetrical? Does it obey symmetry? Symmetry means if ARB is in there, then BRA should also be in there. Okay, so suppose we have the order pair A comma B in the relation. Well, A comma B comma C comma D in the relation. So we have this order paired here. Okay. Then it follows that by the definition of relation, we have A times D is equal to B times C. So A times D is equal to BC. That is true. I don't think anyone will argue with that. Any questions on that? Okay. However, we want to eventually show, and I'll do like a little side note here. If this is symmetrical, we want to show that the order pair C comma D comma A comma B is also in the relation. That's what we want to show. I want to show that that order pair C comma D comma A comma B is in the relation, because that's what it means to be symmetrical, right? You're pretty much just switching these two, because that's literally what we did here. AE and EA should both be in the relation if it's symmetrical. AB comma BA should be in the relation. Okay. Well, notice something about this. AD, and already here, AD is equal to BC is the same as BC is equal to AD. Does everyone agree with that? I'm sure not. Okay. So this was then, it follows that Well, notice that your relation states this. If the ordered pair is in the relation if and only if AD is equal to BC. But it's a biconditional statement. So far I've been going in this direction. But I can also go in the opposite direction, which means if I have this scenario, I can go back to this. Well, I do have that scenario right here. So that means that's the same thing as saying, well, hold on. I have to change it a little bit. It follows that BC is the same thing as saying CB. So we have CB is equal to AD. Thus, now we can say CD comma AB is in the relation. Oh, wait, hold on. We have CD and DA. Oh, yeah, that's the same thing. AD. I could change it to DA just so I can make it better. So I can make it match. So it is symmetrical. Does everyone see that? I should probably write that out so it could be a little bit more precise. And the reason why I'm trying to make it precise is because I'm trying to match it exactly how it's done here, where they have AD times BC. So I'm trying literally to do the same thing. AD, BC, and that's what I'm doing here. CB, DA. Any questions so far? Any questions? Can you show an example when numbers after? Well, it's the same thing with numbers. So you can put these any numbers. These could be any numbers you want. So it doesn't really matter. Okay, 3. Is it transitive? So A R B and B R C, then it follows A R C. So this is what transitive means. A R B and B R C, then we have A R C. Well, actually, these are numbers, by the way, because that's what I said. Let R be the relation on a set of ordered pairs of positive integers. So all of these are numbers. We're just not we're letting them be represented by some variables. Because we can't just say, oh, 1, 1, and let's say 2, 2. Why? Because that's only one example. And I need to show that it works for every scenario of this form. That's why we can't really use, I see what you're saying by numbers now. We can't really use numbers like actual numbers. It has to be represented by something else, which in this case, we're using these variables to represent the ordered pairs of any positive integer. Now, unless we have a relation that consists of, like, let's say 1, 2, 3, 4, or less, then yes. Well, not a relation. If we have a set that consists of 1, 2, 3, and then we have our relation, which will be 1, comma 1, 1, comma 2, 1, comma 3, 2, comma 1, 2, comma 2, 2, comma 3, and the other ones, then yes, you can show that that relation is an equivalence relation. And then that's another example with numbers. Okay, now there's a transitive. Well, to show transitive, we need this. So we need an A, we need a B, and we also need a C. So suppose we have, or suppose the order pair A comma B and C comma D is in the relation, and the order pair C comma D and E comma F is also in the relation. Then that means A times D is equal to B times C, and C times F is equal to D times E, respectively. So if we're trying to show that this relation is transitive, what should be the end result? What am I trying to get at the final end? What two order pairs together am I trying to connect? AD and BC? Not quite. Be more specific. What do you mean by the first two sets? So in other words, what am I trying to show here to show that this is transitive? What am I trying to show so that that is transitive? What do I need to eventually show? We need to show what? A comma C, not CE comma FD. You're close, but not CE comma FD. You're close, but not ACE comma FD. A comma C, not quite either. AF is equal to BE, YF and AF is equal to BE. What does that give you? What two order pairs are you trying to connect? You're right there, you have it. Right there, you have it. You just have to tell me what order pairs are you talking about? So AF is equal to BE is true, but what order pairs are you talking about? Exactly. I need to show that A comma B and the order pair E comma F, this order pair of order pairs is in the relation. If I can show that, then I can show that this relation is transitive. And that's the whole thing with all of this. You have to like, what is it that I have to show at the very, very end? What is it that I need to do so I can show that this is true? So you're right. We have to show AF is equal to BE. How do I get for AF to equal to BE using only this information that I have? How can I get to that? Any ideas? How can I get to the fact that AF is equal to BE? How can I get to that? Any ideas? Based on only the information that we have. use D somehow? How would you use it? What would you try and do? You can use D somehow, but how? How can we use D since that was suggested? And use C and D since it's both using properties. Okay, but how would you use them? That's what I mean. You guys are saying use this, but how do we use that? What do we do? How can we use C or D? No? Okay. Well, using D or C is actually a good idea. The thing is, how do we use it? Well, notice that all of these are nothing but positive integers. So none of them are any other integer that's not positive, which means these ordered pairs do not have zeros. None of them are zero because zero is not positive. So that means that since these are integers and none of them are zero, I can divide by them. I can say, okay, let's look at AD is equal to BC. This is the same thing as saying D is equal to BC over A. Right? So that's one way how I can use D. Or what I could have done instead, I could have said this. AD is equal to BC. And then I can multiply both sides. Multiply both sides by, let's say, CF. So we have CF AD is equal to BC. But then CF is the same thing as saying DE. Like that. All right. So notice that the C's cancel out. So we have CFAD equals DEBC. I notice, wait, I can cancel out the C's and the D's. And I'm left with FA is equal to EB. But this is the same thing as saying FE is equal to BE. Which means if AF is equal to BE, then it follows that the order paired A comma F comma BE, oops, not A comma F, A comma B comma E comma F is in the relation. Which means that if we have this and this, then in the end, this and this, which is your A and C, is also in the relation. So R is transitive. Therefore, R is an equivalence relation. So R is an equivalence relation. Any questions on that? And that's how you show a relation is equivalence. You have to show it's symmetric, reflexive, and transitive. And that's what we did. We showed all of that. It is reflexive, symmetric, and transitive. So this relation is an equivalence relation. Okay, let's move on. Now, since we already know what an equivalence relation is, now we can define an equivalence class. Okay. Let R be an equivalence relation on a set A, the set of all elements are related to an element A of A is called the equivalence class of A. The equivalence class of A with respect to R is denoted by open bracket A, close bracket A, subscript R. I have to get my charger because my laptop is about to run out of battery. I don't want you guys saying that classes ended early. Okay, so let R be an equivalence relation. And I said, hey, the set A of all elements are related to an element of A is called the equivalence class of A. The equivalence class of A with respect to R is denoted by this. Let's go back to the relation we know about, which is this one here, which is the set of ordered pairs of positive integers. Okay. So that relation consists of 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. This goes on forever. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. This goes on forever. 3, 1, 3, 2, 3, 3. Actually, no, wait, hold on. I'm talking about my set A, not R. Okay, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, blah, 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 3, 6, blah, 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 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, blah, blah, blah. And this goes on because obviously there's an infinite number of positive integers. So this is my original set A. Okay, here's my original set A. The pairs of positive integers. Now, a relation, let R be an equivalence relation on a set A. So, one relation I could think of will be, like, for example, R could be the set of 1, 1, 1, 2, 1, 1, 1, 3, 1, 1, 1, 4. Actually, no, it wouldn't be that. It has to be true that it has to be, sorry, it has to be true that A, what has to be true? Oh, AD is equal to BC. Okay, so 1, 2, 2, 4. 1, let's see what's another one. 1, 2. Oh no, then there'll be 1, 2, and then 3, no, not 3, 6, 3. Do I want 6? No, what do I want? Yeah, 6, 3. That is true, because then that would be, no, that wouldn't be 3. It will have to be 3, 6. Because then this will be 6, and this will be 6. 1, 4, or 1, 2, comma, 4, 8. Because then this will be 8 and this will be 8, so that will equal. And you can do this forever. The same thing with, let's say, 2, 2, and we have 4, 4. 2, 2, we have 6, 6, and so on and so on. So this could be done forever, and same thing. So we can have a big relation that consists of all those terms. Now, what does an equivalence class do? Okay. Now, let me give you an example of an equivalence class. Notice that for this relation, for that relation, the rule is AD is equal to BC. right? Okay. Now, notice that all of these here, these ordered pairs, are A comma B. So I want a relationship with A and B here. So this is the same thing as saying A over B is equal to D over C. Now, why is this important? Well, because now I'm saying that any fraction in there should be the same. So these two will give me two fractions are equivalent. Okay. So my equivalence relation of 1 comma, let's say my equivalence class of 1 comma 3 will be the set consisting of 1 comma 3, 2 comma 6, 3 comma 9, 4 comma 12, 5 comma 15, and so on and so on. Why? Because if I do this, if I combine this one with this one, I'm going to get 6 is equal to 6. If I combine this one with this one, I get 9 is equal to 9. If I combine this one with this one, 12 is equal to 12. So it still obeys the relation, which is this here. Pretty much what I'm doing, I'm getting all the ordered pairs that reduces to the fraction 1/3. And notice that that will give me the set of all elements are related to an element of A is called the equivalence class. So notice that all of these things here will belong in the original set of A. Do you see that? All of these will belong in this original set. We can have another equivalence class. Let's say we have the equivalence class 2 comma 5. Well, as long as it obeys the same rules of the relation, it'll be 2 comma 5, 4 comma 20, 6 comma 15, 8 comma 40, 10 comma 25, and so on and so on. And all of these elements are also part of element A, which is the original set. Any questions on this? And it's possible that this relation can have these, because again, there could be different types of relation for a set A. It doesn't just have to be one single one. This could be just one of them. Maybe this set is not even in this one, but definitely these elements are in the original set A. Any questions? Okay. Now, does this have to be 2 comma 5? No, this could have been 6 comma 15. The equivalence class 2 comma 15 is the same equivalence class as 6 comma 15. They're the same, or the same as the equivalence class 4 comma 20. In other words, this acts as a representative of this set, but this is nothing special about this representative. It could be this one, this one, this one, this one, or that one. It doesn't matter. Same thing with this. This could be the representative of this equivalence class. This could be the representative. This could be the representative, this one, or even this one. In the end, you're going to get the same set. So it doesn't matter which one's the representative. In the end, you're still going to get the same thing. So this doesn't come from anywhere. It could be any one of these elements that represents this entire set. We could do another one. We could do, let's say, the equivalence class that deals with the fractions reduced to, let's say, 1 comma 4. So we have the order paired 1 comma 4, 2 comma 8, 3 comma 12, 4 comma 16, 5 comma 20, and so on. In the end, what do you notice about these equivalence classes? What do you notice about their elements? Are they all the same? Are they all different? Do you think they're going to share an element in common? They should be different, right? All of these should be different. In terms of what I'm saying is all of these equivalence classes should all be different sets. They all should contain different elements. None of them should be exactly the same unless they come in from the same set like this. But they should all be different, meaning if you intersect any one of these two, they should have nothing in common. It should be the empty set. If you intersect these two sets, or even these two sets, or even these two sets, the intersection of them should be the empty set. Now, the other thing that it's doing is, if this is my set A, here's my set A. My set A consists of all those pairs. These are my equivalence classes. Notice that this is a subset of A. This is also a subset of A, and this is also a subset of A. Does everyone see that? All of those are subsets of A. So what is each equivalence class doing to A? Technically, what is each equivalence class doing to A? If my set A originally was this, what does it seem that my equivalence class is doing to A? What are my equivalence classes doing to A? Or what does it seem to be doing to A? So let's say I have another equivalence class. Let's use this color. Let's say we have the equivalence class that all reduced to 7/10. Well, we have order pair 7, 10, 14, 20, 21, 30, 28, 40, 35, 50, and so on. And this is still a subset of A. So what is my equivalence class doing to the set A? Or what does this appear to be doing to my set? Anything? Maybe what if I rephrase it this way? If I unionize all of these, if I put all of these together, if I'm going to put all of these equivalence classes together, meaning I union them, what is it going to give me in the end? If I combine all of these equivalent classes, what is that going to give me at the end? If I write every single equivalence class down, and I combine them all, what are they going to give me? Set A, exactly. So what each equivalence class is doing is actually breaking A apart. That's what it's doing. All of these equivalence classes are giving you sets where each element belongs in these equivalence classes. But these elements came from elements of A. So these equivalent classes are breaking down A. So if you look at A, like let's say A is a big old thing like that, you're breaking it apart into equivalent classes. We'll call this A sub 1, A sub 2, A sub 3, A sub 4. So here's A sub 1, here's A sub 2, here's A sub 3, here's A sub 4, and so on up to how many A sub n's you have. In other words, what you're doing to the original sets is you're partitioning it. That's what you're doing. You're partitioning it. So the equivalence classes partition the set, or that's what it appears to be doing. It pretty much breaking down the set A into disjoint subsets. Because notice that each one of these sets is a subset of the original set. And all of them are disjoint. What I mean by disjoint is that if I intersect them, they have nothing in common. You will always get the empty sets. So we'll stop here. We're not done with this, obviously. So take a 5-minute break and then we'll continue. If you have questions, let me know. Or when something's being partitioned, well, if you have in a computer, you partition at times. Like let's say you want your computer to run Linux, Apple software, Ubuntu, and Windows, you probably partition the memory. Most likely. If you want your computer to run all of those. So you probably have like big memory space and you partition it. With equivalence relations. In terms of I really don't know, honestly. The only way I could think of is if you're trying to organize something or order something in specific categories. And you're breaking it down to equivalence classes. And the equivalence classes represent all of them that relate to this. Like let's say you're relating people to X person is older or equal to the age of this person. And then you break apart that set into equivalent classes of, let's say, anyone who's of this age, anyone who's of this age, anyone who's of this age. That's what I'm thinking about right now. Okay. Now, so let me rephrase this because I think you guys, some of you might be a little confused. So an equivalence class, all an equivalence class is this. It's going to contain elements that are related to the set of A. So if this is your set A, for the example that we've done, so let's forget about this. Maybe this part's confusing you. This are the elements in set A in the relation that we were talking about here. The ordered pairs of positive integers. So all of these are the ordered pairs of positive integers. Whichever positive integers you want to think of, it's in here. Okay. An equivalence class is going to contain some of these elements. All you're doing is just separating it in a certain category. So what I'm doing is I'm trying to make a relationship between A and B here because I know that the ordered pair here is A comma B. Okay. So my relationship is this. If I know that my relation has to obey this rule, then since they're all positive integers, I can divide by them. So AB is equal to DC. So in other words, I want two things that give me the same fraction when I put them under one another. So if I have A comma B and C comma D, these are two ordered pairs, I want A over B to equal the same thing as C over D. That's what I want. So that's literally what I'm doing. So here, 1 comma 3, that means I'm looking for, when I put in ordered pair as a fraction, it should reduce to 1/3. So I'm getting all the ordered pairs that are reduced to 1/3. And notice that these ordered pairs are not all of them of here, just a couple, only a couple. Same thing here. I want all the ordered pairs that reduce to 2/5. Well, 2/5 is 1. 4/20, 4/20 is 2/5. 6/15, that's 2/5, and so on and so on. Same thing with the 1 comma 4. I want all the ordered pairs that reduce when you write them as a fraction to 1/4. And here, all the ordered pairs that when you write as a fraction reduce to 7/10, and so on and so on. Okay, so these are the equivalence classes. But what the equivalence classes are doing to the original set, it is separating them into their own sets. In other words, all of these are subsets of the original set. So if I combined all of these sets, I should get back the original set. So if I was able to write every single equivalence class down that has to deal with the relation R and combine them all, I should get the original set. But because the equivalence classes is breaking down the original set into disjoint subsets, because all of these are subsets of the original set, and they're all disjoint, meaning they have nothing in common. Then what we're doing is we're partitioning the set. The set is being partitioned. So a partition of a set S. Shouldn't 4 comma be 4 and 10 instead of A sub 2? Did I mess it up? 4 comma 20. If I multiply, oh, you're right. That should be 4 comma 10. Thank you. Thank you. Thank you. Thank you. I messed up my basic math. Thank you. You're right. This should be 4 comma 10. Yes. Thank you. Okay. So a partition of a set S is a collection of disjoint, non-empty, subsets of S that have S as their union. Now, the collection of subsets A sub I, where I is an element of I, and what we mean by I, capital I here, is like 1, 2, 3, 4, depending on how many subsets you have. Oh, 8, did I mess it up? For 8, that should be, oh yeah, that should be 20. Thank you. I wrote it too quickly. Okay, so we have forms a partition of S if and only if, first condition, all of these subsets are non-empty for I being an I. So none of these subsets should be non-empty, none of them. So if you notice at these subsets here, which are the equivalence classes, none of them are non-empty. They all contain something, which I. Second condition, the intersection of any of these two subsets should be at the empty set when I does not equal to J. So if these subsets are different, and you intersect them, they should have nothing in common. They should have nothing in common. And a final condition, if you take the union of I as an element of capital I, A sub I is equal to S. So if you take the union of all of these subsets, you should get back the original set. So for example, let's say we have the relation, well, not the relation, the set S, which is A comma B comma C. Then suppose we have the relation A comma, well, let's say 1 comma 2 comma 3, and we have the relation 1 comma 1, 2 comma 2, 3 comma 3. And this obviously is an equivalence class. It is this relation here. It is reflexive, it is transitive, and it's symmetric. It follows all of those properties. Now, let's say the equivalence class 1 of that relation is just going to give me the set of 1. That's it. If I do the equivalence class 2, that's simply just going to give me 2. If I do the equivalence class of 3, that's simply going to give me 3. Notice that if I intersect any of these sets, they don't have nothing in common. None of these sets are empty sets. But if I combine them all, if I do the union of set 1 of the equivalence class 1, equivalence class 2, which is this set here, and equivalence class 3, this will give me 1, 2, 3, which is the original set. So pretty much visually, if you want to see this visually, here's set S. I broke it down into set that contains 1, and a set that only contains 2, and a set that only contains 3. So a collection of these subsets partitioned S. Okay, so we have a result this theorem. 9.5.2. Let R be an equivalence relation on a set S. Then the equivalence classes of R form a partition of S. So all it's saying is this, that the equivalence classes form a partition of S. Okay. So let R be an equivalence relation on a set S. Then the equivalence classes of R form a partition of S. However, going backwards, conversely, given a partition, A sub I, such that I is within capital I, of the set S, there is an equivalence relation R that has the set A sub I, where I is a capital I, as its equivalence class. So given a partition of the set S, there is an equivalence relation that has the set A sub I as its equivalence class. Any questions so far? No? Okay. That pretty much ends section 9.5. Okay. Now let's go to 9.6. Just checking if anyone has any questions. That's why I'm going a little slow because I'm looking at the chat to see if anyone has any questions. Hopefully that cleared it up for some of you, and hopefully it didn't confuse you. Okay. Now, 9.6, we're still going to be talking about relations. This whole chapter is about relations. But 9.6, we're going to be talking about different type of relation, okay? We talked about relations that are referred to as equivalence classes if they're symmetric, transitive, and reflexive, okay? Now, 9.6, let's start off here. Talks about another type of relation. So let's look at a specific relation. Let's suppose we have this question here. Let me write down the question. Is the divides relation on the set of positive integers an equivalence relation? Is the divides relation on the set of positive integers an equivalence relation? Now, what do I mean by divides? For example, A divides B. So an example of that, 2 divides 4. Okay. Well, first, let's find out. Is it reflexive? I don't know why I wrote it like that. Is it reflexive? Is the divides reflexive for a set of positive integers? So ARA, is it reflexive? Well, A divides A. Well, let me rewrite it like this. A divides A holds true. Yeah, if we take any integer and it's a positive integer where A is some positive integer, just to reiterate that, then A divides itself. Yeah, that makes sense. A does divide A. That's true. I don't have to prove that's true. If you want to do a quick proof of it, well, if A divides A, then that means A is times some M is equal to A, where M is some positive integer, right? But the only way this could be true is if M is equal to 1, right? Which means, okay, A is equal to A, so A must divide itself. Does everyone agree with that? So A is equal to A, hence A divides A. Any questions? Okay. Is it transitive? Well, if it's transitive, it has the rule A are B and B are C, then A are C. That's the rule. If it's transitive, then this is going to happen. Okay, so suppose we have A divides B and B divides C. Well, we have already proved this many times. Then A divides C. So it is transitive. That's true. We're not going to prove that one because we already done it before. Well, and right now we're just doing the notes. So you can go back to your notes and see that, yeah, we have done this before. If A divides B and B divides C, then clearly A is going to divide C. Okay, so I know it's transitive. The question is it symmetric? If A are B, then B are A should also hold. So is the divide symbol symmetric? Is it symmetric? Well, if it's symmetric, that will mean that A divides B. If A divides B, then B divides A. Is this true? If A divides B, then B must divide A. If it's symmetric, this has to hold. Does this hold? Why is it true? I'm not saying you're right, nor am I saying you're wrong. All I'm saying is, why is it true? Because they're all positive integers, right? And they can all be divided into each other. But remember what we mean by divided, it divides evenly, meaning there's no remainder. Because that's the definition of divides. It divides in nicely. So, okay, why is it not true now? Okay, so give me an example that where it fails. If A is equal to 2 and B is equal to 2. Okay, let's see. If A is equal to 2 and B is equal to 1, then we know that 1 divides, or you're technically saying 2 divides 1, then 1 divides 2. Not quite, because 2 doesn't divide 1. So, but let's switch them around. Let's say A was 1 and B was 2. Okay, if we switch them around, 1 divides 2, but 2 does not divide 1. So it is not symmetric. Not symmetric at all. But can this ever be true? Can this statement ever be true? If so, how can we make sure that statement is true? How can we make sure if A divides B, then B will divide A? How can we make sure that that statement does come out true, though? Because you're right. Right now, it's not true at all. It doesn't hold, so it's not symmetric. So already, this divide symbol is not an equivalence relation. But if we do want this to be true, how can we make this statement to be true? And I should probably write it number 1 so you don't get confused with the divide symbol. If A and B are the same, exactly. However, if A divides B, then B will divide A. No, sorry, let's rephrase that. We know that A divides B and B divides A. Oh, hold on. Let me read that. If A divides B and B divides A, then A must have been equal to B, which means this is only true when they're the same. So A and B are not distinct. Now, this is interesting because this can hold, assuming that these are the exact same thing. That's not called symmetry, though. What is this called? It has a specific name that you have seen before. When the pairs are not distinct. What is that called? Not reflexive, not reflexive. Because we already showed that reflexive holds. So it's not necessarily reflexive. But you're close, you're in that realm, but it's not reflexive. It goes back to section 9.1. And 9.2. It's clearly not, that does not mean transitive, so it can't be transitive either. Anti-symmetry, right? So this is anti-symmetric, and that's the important one. So it is anti-symmetric, it is transitive, and it is reflexive. So the divide symbol, it's not an equivalence relation because it's not symmetric. However, it is reflexive, it is transitive, and it is anti-symmetric. So when those three conditions happen, you don't have an equivalence relation. What you have instead is that this relation is called a partial order. So the divides, what did I call it? The divides relation on the set of positive integers is not an equivalence relation, but it is a partial order set. It is a partial order set. Okay, now I'm going to give you the definition of that. Definition. A relation R on a set S is called a partial ordering or partial order if it is reflexive, antisymmetric, and transitive. And that's the important one, antisymmetric. So if it's not symmetric, then it's not an equivalence relation. But if it's antisymmetric, reflexive, and transitive, then it's a partial order set. And again, for it to be an equivalence relation, it needs to be reflexive, symmetric, and transitive. So that's the biggest difference between an equivalence relation and a partial order set. One is symmetric, the other one's antisymmetric. Now note that a set S together with a partial ordering R is called a partially ordered set, or for short, post set, partially ordered set, and is denoted by the order pair S comma R. Members of S are called elements of the post set. So by that definition, a set S together with a partial ordering R is a partial order set or a post set. So notice here that for the divides symbol, we did use a set for it. And the set was a positive set of positive integers. So I will write it like this. Oops. The set of positive integers, and the symbol for divides is a post set. That's how we'll write it. Any questions? Okay. Now, if we look at this relation of divides, let's say the relation is 1 comma 1. Actually, make a 1 look like a 1. 2 comma 2, 3 comma 3, and so on. And then let's say we have 2 comma 4, 2 comma 6, and so on, 3 comma 6, 3 comma 9, so on and so on. Okay. Now, 2,6 is in this relation. If we're doing the same relation, the relation of divides. So this is the relation of divides. 1 divides 1, 2 divides 2, 3 divides 3, and so on and so on, making sure it's reflexive. 2 divides 4, 2 divides 6, 2 divides whatever, 3 divides 6, 3 divides 9, and so on, to make sure it's transitive. 2 divides 4, and let's say 4 divides 8, and 2 will divide 8 and it'll be in there somewhere. And I'll make sure it's anti-symmetric, meaning 4 divides 2 will never be in there. So, or 6 divides 3, 9 divides 3, 6 divides 2. None of those will be in there. So it could be anti-symmetric. Okay. So 2 divides 6. So 2, the order pair 2,6 is in the relation. I can also say the order pair 5,15 is in the order relation, and so on and so on. To denote this is the notation we use. So to discuss, well, actually, let me say, to denote this, let me write it out. The notation A, and this is going to look like a less than or equal to sign, but it's not. So less than or equal to looks like this. This is more like a script, kind of like drawn more like a curvature to it. Is used to denote that the order pair A comma B is in R in an arbitrary pose set. So the notation A, and you'll hear me say less than or equal to at times, just to say, look, this is why I'm writing it out, is used to denote the order paired in an arbitrary pose set. Okay. And we will be using the symbol for the rest of this section. So make sure you get used to it. And again, don't make it look like a less than or equal sign, because it's not. It's more like a little like that. That's why I'm trying to draw really, really slowly. Because if you draw too fast, it may look accidentally like you're less than or equal to sign. Okay. The elements. Misspelled elements. The elements A and B of a pose set S comma, and then that symbol there, are called comparable if either the order pair A comma B or the order pair B comma A is in the relation, or I should say in the pose set. However, when A and B are elements of S such that neither the order paired A comma B or nor the order paired B comma A is within that relation. A and B are called incomparable. So let me give you an example of that. So in the relation of divides, our set S, so let's go back to that relation. So the relation looks like this. The post set, I should say. That's what it looks like. Our set S in this scenario is the positive integers. And this is the relation. Okay. Now, God, that looks too much like less than or equal to. Okay. Now let's take two elements in S. Okay. So let's look at two, the symbol that signifies the order paired 2, 4. Well, we know that 2 comma 4 is in that relation. How do I know that? Because 2 divides 4. So far, so good. However, this, so 2 and 4 are comparable. So let me write that out. So 2 and 4 are comparable. However, let's say 7 and 10. Well, the problem with 7 and 10 is that 7 and 10, both of these do belong in S. They're elements in S. They're both positive integer. But 7 does not divide 10, nor does 10 divide 7. So 7 and 10 are incomparable. That's what incomparable means, and that's what comparable means. Now you will also see this symbol here without the bottom thing here. So you'll see it sometimes like this. And it does look like a less than or equal sign. Less than or equal, actually not less than or equal to. It does look like less than. So this denotes A is less than, A is the order paired, A and B is an R, but A does not equal to B. So that's the biggest difference. Also, we say A is less than B, or B is greater than A if A, using that symbol, is less than B. Now, the reason why the symbol that's similar to less than or equal to is used is because one of the most partial orders that would use, or actually it's a total ordering, is the less than or equal to relation. Like literally the less than or equal to relation. That is an example of a post set in the set of any integers that is totally ordered. And it makes sense. A is less than or equal to B. If B is less than or equal to C, then A is less than or equal to C. It's transitive. If A is less than or equal to A, well, A is less than or equal to A because A is equal to A. So it's reflexive. A is less than or equal to B, but that's it. There's no B less than or equal to A because it's not symmetric. The only time that A is less than or equal to B and B is less than or equal to A holds if A and B are exactly the same thing, which means it is anti-symmetric. So that's an example of a set that's also total ordering. So that's why that symbol for less than or equal to is used. Now, if you're wondering what I mean by a total ordering, this is what I'm saying. If we have the post set, where this could be any relation, this is what this represents, any relation, is a post set, and every two elements of S are comparable, S is called a totally ordered or linearly ordered set. And the symbol that I'm indicating represents any relation is called a total order or a linear order. A totally ordered set is called a chain. And the best example of that will be the post set of positive integers and the less than or equal to symbol. Because this will hold for every two elements in S. So any two integers, like let's say we get 1 and 5. Well, 1 is less than or equal to 5. This is true. If I get 1 and 2, 1 is less than or equal to 2. Yes. If I get 2 and 20, 2 is less than or equal to 20. Yes. If I get 2 and 2, 2 is less than or equal to 2. Yes. So no matter what two elements are in this set, in the integers, any integers, could be even negative numbers, -3 and 0. -3 is less than or equal to 0. This holds. All of these elements are comparable, all of them. It's not like the one with the division where 7 and 10 are not comparable. Yes, they belong in the positive integers, but they don't hold with respect to that relation. Here, every two elements will hold, no matter what it is. So because that is true, this post set is a totally ordered set. It's a totally ordered set or linearly ordered set. And this is called a chain. A chain. Any questions? We're not done with this section, but we're running out of time, honestly. But any questions? Oh, this is the last section for chapter 9. That's it. Oh, chapter 12. I think it's like 4 sections that we're gonna do. It might have more, but we're only gonna do 4 sections. Well, we still have enough time. Good. All right. I'll see you guys next week. Remember, there's no class on Thursday. Have a good weekend, and I'll see you guys next time.